I want to talk about why the wave waves. It's like a kid's story, isn't it? Why does the wave wave? Why did the wave wave? And it is to do with stability. I'll use green for neutral, red for warm, blue for cold. If you blow the air onto a hill and you lift it, what happens to the temperature of the air mass?
Got to cool as it rises.
It cools as it rises. Okay. Now, that hill's there. I want you to imagine that the hill's there, and we're going to compare the temperature of the air going over the top of the hill to the air alongside the hill, where there isn't a hill. Okay, just bear with me. It's a little bit difficult to visualise. What can I use to be a hill? That'll do.
I was going to suggest you get Owen to stand.
Get Owen to lie on the table. Okay, so
What did a hill, not a mountain?
I'm going to really enjoy it in WA. Right. So here's the air coming on to a mountain. It's got to go up over the mountain. The air that goes over the mountain will cool. So the air here is coming up and it's cooler. If you compare the air at this altitude here right now with the air that hasn't gone over the mountain, that's neutral. That's the neutral environmental temperature. It's quite likely to be colder. I'll draw that in terms of a T-fight. Let's say that this is the temperature of the air mass as measured. So temperature along that axis, altitude along there. You know that if a thermal forms, it will run up and it will cool at 3 degrees 1,000 feet. We know that. Yeah, that's straightforward. That's basic gliding. But what is also true is if you take this air mass here and you lift it, it will cool at 3 degrees 1,000 feet. And if you drop it, it will heat at 3 degrees 1,000 feet. Just forget the influence of cloud at the moment, because that just complicates things. So what we've done here, we've taken this piece of air and we've lifted it, and therefore we have cooled it. And the difference between the air temperature here and the temperature of the air off the mountain is the difference between this air temperature here, this point here, and the air off the mountain. Yes? It's cooler than the air around it. If it's cooler than the air around it, it is fundamentally denser and therefore subject to gravity pulling it back down again. This is stability. Yeah? You grab this piece of air, you lift it up, it's too cool to be here, it's too heavy. You let go, it comes down again. That's stability. So as the air flows across the top of the mountain, having been lifted, there is a restoring force, and that restoring force, which I'll draw in blue because it's cold, it's due to it being colder than the air off the wave train, pulls it back down again. That's the elastic that pulls the air back down again. As it comes down, as the air mass is bent down, it doesn't just go like that, because it has momentum. Once you have a decent wind blowing, you have considerable momentum. I mean, even a thermal has momentum up, or a down current has momentum down. But this is moving with maybe 40 knots of wind. You imagine the wind blowing over the Ben Oha range. You know, if one thermal is 80,000 tonnes of air, the whole mass of air blowing over the Ben Oha range and down the far side, you're talking trillions of tonnes of air. You're talking immense amounts of mass. So once it's bent downwards, it overshoots its neutral point because of the momentum. And therefore, as it comes down, the opposite is happening. The restoring force that way is due to the fact it's warm. So the air's come down through its neutral point, it's come down the other way, it is warmer than the air around it, and that is the force that restores the air mass to its neutral altitude. So the wave is caused by temperature changes. How do we know this? Because of the behaviour of the air mass underneath the wave. And we'll talk about that in a moment. So, as an analogy, you imagine a vibrating guitar string. The tension in the string is what restores the string to its straight and level position. But the mass of the string is what takes it past its straight neutral position into the other oscillation. So a piano string, I know something about piano strings, or a guitar string will keep oscillating for some time. You could get deep into mathematics with this. Fortunately for you guys, I don't speak mathematics, so you know, I can't even work out a simple equation myself, but I can fly the wave. So you get this oscillation. There are a couple of terms that are worth mentioning here. I'm not going to draw the colours now. This is the wavelength. The stronger the wind, the bigger the wavelength, the longer the wavelength. That seems to be a fairly straightforward, standard, easy to understand rule. This is the amplitude of the wave, from the top to the bottom. I don't know what controls the amplitude. It's some fairly subtle factors about stability, density, temperature, all those, and you can write an equation to describe how amplitude is controlled, but I don't understand the maths. I just don't understand it. So I don't understand what controls the amplitude, don't ask me. But the combination of the wavelength and the amplitude tells you about the shape of the streamline. For instance, if you have an amplitude that much and a short wavelength, the streamlines will be steep. If the wavelength is long, the streamlines will be shallow. Yeah? Okay. Generally, when the wind is light, because the wavelength is short, the streamlines tend to be quite steep. So even though the wind is light, the air goes up and down at a quite a steep angle, so you can soar it. That means you can soar wave down to sort of 10, 12 knots of wind. Just creeps down, creeps up again, and you might get a knot or two of lift at 10 or 12 knots of wind. If it's howling, if you're flying in 80 knots of wind, which we've done, I think the highest wind I've seen is about 100 knots, which is just impossible to operate in. If you're flying in 50, 60 knots of wind, you'll have a long wavelength, and therefore the streamlines are likely to be quite shallow, and you still only get a few knots of lift. Typically you can get up to 3,000 feet a minute in wave, but I've only seen that in Scotland actually. The strongest wave I've seen here is about 2,500 feet a minute, something like that. The Tyree Pet that forms down there, that's the picture on the side of the clubhouse here, commonly gives 3,000 feet a minute plus. It's just insane. Alright, so wavelength, amplitude, streamline shape. I'm interested in the shape of the streamlines. If the shape of the streamlines is steep, then generally it's going to be pretty good. If the shape of the streamlines is shallow, then generally it's not. And the other thing you have to understand about working in wave situations, imagine this is oscillating, maybe the vertical component of this streamline, that is the vertical component, is, let's say, 300 feet a minute. So you've got 300 feet a minute down and 300 feet a minute up. That's symmetrical, but of course as far as you see it in the sailplane it's completely asymmetric. That is, if you're flying in 3 knots of rising air, the vario comes up, you slow right down, and the vario comes up and you can get about a knot and a bit of lift. Just really, Lemmy always does this, he goes, he's got this habit going on. So you go up really, really gently. So in the sailplane, that gives you plus 1.2, something like that. Oh, wrong side. Flying in this bit, the vario's down here, like -5 to start with. So you accelerate and you do 80, 90 knots, and the vario's down here, and that's like -8. So it's profoundly asymmetric as far as we're concerned. Okay? There's this offset because of the sink rate of the sailplane. Really worth considering. So, just like riding a bicycle, you've always got a built-in headwind with a bicycle, so you get more headwinds than tailwinds. When you're flying a sailplane in the wave, there's always a lot more sink than there is lift. A lot more sink. When the sink is extreme, when you've got maybe a 50 knot headwind, and you've got maybe 2,000 feet a minute sink, and you're flying 130 knots to deal with it, your glide angle into wind in the sink of a wave is frankly just appalling. Sometimes you are going nowhere. You can barely penetrate. You're just going, and you've got to think of another way to get from here to there. That's quite important. Okay, so getting into the wave. I'm going to draw in green the top of the thermal layer, the convective layer, above which there will be a bit of an inversion and the air will be very stable. You'll notice that the air comes down behind the hill, but it actually starts coming down fractionally in front of the hill, and on the top of the hill that it's actually started to descend. If you have a good wave day with a big mountain and the top of the convective layer near the mountain, that is the shape of the flow. The inversion starts to come down. The air actually starts to come down here. It's because this can't rise up because it's heavy. This is heavy in relation to this. This can't rise up. And so you tend not to get the thermals off the hill coming up here. If there's a good solid inversion in a good wave day and a good tall trigger, you'll be in a situation where you don't get proper thermals off the top of the hill. This is quite important. What you get instead is a little compression on the top of the hill. This is so heavy that that can't rise up. But this has risen up. This is the flow at low level. And this is the flow behind the hill like that. Now that conflicts very slightly with what I've said about the shape of the way wave is formed. But this is actually what's happening. Again, I don't have the maths or the physics to explain it in greater depth, but you can see by the shape of what we've drawn on the board. If you're trying to soar on this hill, then you'll get thermals coming uphill here. You'll get a little bulge, maybe like that in the inversion. But you won't get good thermals coming up here. They'll get smashed up. They'll get smashed up by the wind blowing over the top of the hill. So that's typical for ridge soaring in a situation, ridge and thermal soaring in a situation where there's a hard inversion and good wave. Here, what happens is the wind comes hammering down the hill. Here, the depth of the convective layer increases. The air is coming down, heating, turning around, going up, cooling, down, heating. So the airflow above is doing this. Let's draw it again in a neutral colour. Let's draw the air mass up here. Okay, so this is the motion of the wave. And you're trying to get into that. The airflow downstairs is doing this. It's speeding up down here. Here it's gently rising up and slowing down. Here it's accelerating, speeding up. Here it's quite windy. Here it's... This is the inversion. This is the top of the convective layer. Look how the top of the convective layer is going up and down. here where the convective layer has come right down, the wind is strong. The top of the thermals is quite low. Here the wind is light, the top of the thermals is higher. The best place to get climbs is here. Now when you fly here, the glider will move in the wind. But the best place to get climbs is this sort of area. You might find that you can climb up here or here, but generally here you're not going to get climbs going up like this because you're flying in a down current, general sink, and you're flying in a strong wind. So the thermal production here is shitty. Thermal production here is great. Draw a windsock. That's how it looks in terms of the winds on the ground. So, windy, low inversion, no wind, high inversion. It's a no-brainer. The strongest place to find thermals is actually under the crest of the wave, where the convective air mass is the deepest. How do I know this? I've got the Australians to thank for this, because we had some very good days of flying when we had bushfire smoke in this layer. And you're sitting up here in the wave, looking down at this layer, and you can see really clearly, because it's so dirty, the air in the convective layer in this mass, you can see really clearly the air convective layer rising up, coming down, rising up, and coming down. And of course you can also see the patches of strong wind, no wind, strong wind. It's one of the things that is very obvious about wave is when this compresses down, the wind underneath this inversion has to accelerate through the venturi, and it howls on the ground. It just howls. It picks the dust up and it throws the dust into the air. It turns glider trailers over, blows cars off the road, damages houses. You'll see up in the Canterbury Flats, in what do they call it, the Canterbury Plains, there's quite a few trees there that are tied to the ground. You know, they've actually tied the bloody trees to the ground so they don't fall over. And of course they have the shelter belts. It's one thing you notice when you come into this country. Immediately you have these big rows of tall trees, like hedges, but 40 feet tall, there to stop the winds, these winds, blowing the ground away, blowing the sheep over and knocking the sheds over. You put shelter belts around stuff. Okay, so the place to get a climb is here. The place to not bother to try and climb is here. The way that you break into the wave, you want to be out of this air mass, out of the convective air mass. Let's draw the T-phogram. This is the convective air mass. Here's a thermal going up there. You want to be out of this air mass and in the stable air mass where the wave is going on. So you need to get through this barrier. Well, you can't climb through this barrier in a thermal, but you can, if it's waving, fly forwards through this barrier in this direction or backwards through it in that direction. You get up to here, then you can get, by flying forwards, you can get into, or backwards, you can get into the wave. Yeah? This is where you need steep streamlines. If the streamlines are very shallow, and you get up to here, and you start pushing forwards, well, you may or may not make the wave. So if I get the glider to here, and I'm looking forwards, and I'm visualising the wave coming down and up in front of me, and punching through the front of the wave, coming out of this and into here. That's what you're trying to do. So we should look now at how the cloud might look. I've drawn this as a blue situation. Today you're going to get a blue situation, I think. No clouds. When you're flying in blue conditions, your thermal will be topping out right up here, and you'll be able to push forwards. One thing that will happen as the thermal comes up, and something I haven't mentioned, at the top here, there is usually a lot of wind shear. Normally in the convective layer the wind is lighter than in the laminar flow layer. Why? Because there's no mix, or very little mixing here. So there's a wind shear between here and here. Of course what does mix it are the thermals coming through. So if I actually take this away, wrong colour, I want red for thermals. Green for neutral, red for thermals, orange for wave. I can hear the voice of my mentor now, even now, the guy who taught me to teach, saying, use of colour, G, use of colour. Here's a thermal coming up and getting rolled over by the wind shear at the top of the wave. The thermal punches up and the wind increases on the top of the thermal and pushes it over. This little thing here is hugely important in wave flying. That shape is hugely important. The actual shape of the inversion is like this. Because of course when a thermal's coming up, it will just change the temperature profile of the MS here slightly. Warm air coming up here, just changing the level of where the stability is. And the thermal rolls in here. So when you're flying at this boundary, it's very messy in terms of vortices. You've got very messy vortex-laden air. So this is a strong signature of how the wave behaves. Now, when we draw the clouds, you will recognise this shape. I'm going to take this away now, and you have no clues except the clouds. The top of the clouds is the top of the thermals. By looking at the top of the clouds, you can predict where the inversion therefore is. Now, if you join the dots, yeah, see the arch of the cloud? This is quite important. See, we tend to think of the top of the thermals as being cloud base. It isn't. The top of the thermals is the top of the clouds. The top of the convective layer is the top of the clouds. The trick is, you climb up here, you go forwards to here, and you punch out into the wave like that. That is what you do. That's how you get into the wave. This zone here, I'm going to draw where you want to be climbing in thermals. If that's the middle of the wave, the highest part of the wave, that's the rotor cloud. That's the highest part of the rotor cloud, the arch of the wave. The best place to be climbing is to end up here. So one tends to start a little forwards. You could perhaps start here and drift all the way back, or you could do this. It's important to realise that this is transient. All this is moving left to right. So the thermals are consistently going. And at the top, of course, and I'll draw, the cloud is tending to do that. I'm going to draw another one with a bit of a hook in it. You see, you recognise that hook shape that you get when you... So the thermal motion, the motion of the MS here is always rolling across. Now this is why they are called rotor clouds. The conventional drawing of rotor is wrong. This can happen, and does happen at Minden occasionally, where that's doing that. But this down current just doesn't exist. If you had a big roll underneath here, then you'd have 25, 30, 40 knots of sink here. You don't have that much. You have 10 knots of sink. If it was really rolling down here, the sink would be utterly catastrophic and the lift would be enormous. It doesn't do that. What you have instead is vorticity, which is caused by the fact that the wind is less here than here. So you have the air getting filled up with little vortices. those little vortices propagate all through the top of the air mass. So when you're flying at the top of the air mass, you keep flying into these vortices, and the shape of the vortices is like this. The nature of the turbulence they feel then, as you fly through it in this direction, is severely down, followed by up. And the glider goes down like that, boom, like that, whack. It feels like getting hit by God's hammer. Okay, so you need to get up here in the thermals, you need to get forwards to punch into, and of course the inversion is lower here so there's no cloud. You get from here to here. We'll look now at being in this area, just being in this area, and how it feels and how it looks. This line is the inversion. Actually, that's not very realistic, it's probably more like that. Of course, a blue thermal coming up here, and there might be some weaker blue thermals. Just cause another little kick. You've climbed from here and it's been good, and you move out forwards here, and as you move out forwards you're continually ending up flying in opposing currents. Boom, boom, as you fly through the thermals. The glider goes boom, boom, like that. It's almost impossible to centre these little buggers because you're flying into the area where instead of being a bubble coming up with a very usable profile that you can centre that we've discussed, the bubble is starting to become this shape, and the profile of the movement of the air in the thermal is like that. And you section across this and imagine how you're going to centre it. It's a nightmare. It's just horrid. It's really small, there's a lot of dump, and in addition, this is only a two-dimensional diagram, but of course in the 3 dimensions, the warmer air above is blowing and separating and blowing around this and blowing over the top of it as well. So flying in and out of this is very turbulent and very difficult to centre. You're constantly getting great big speed changes, great big heaves of lift and sink, and get knocked around. So really the trick with these thermals is to be high enough from here that you don't have to muck around trying to climb in this bit. You've got the glide angle to punch through it and get away. And the way to deal with this stuff is when you have the lift pull up and then accelerate. When you have the lift pull up and then accelerate. You don't try and turn in these little things. They're just RC. You just can't manoeuvre in them. So get the climb back here, get right up as high as you can, right into the wispies, and get a bit of speed so you can come out here going pull, pull. What drives this roll is wind shear. Lighter wind here, stronger wind here. Because the wind shear is a tilted wind shear, you can punch through it. And essentially every time you pull up, now here, I've been lucky enough to cut into a stronger wind. Yeah? Every time you pull up going in this direction, you have a chance of coming into the freer flow above, which is stronger. Now generally, because of the glide angle of the glider into the wind and the slope of this, you'll spend some time pulling through the thermals and trying to get in. I've only drawn 2 pull-ups here. Generally there might be 5 or 6 or 10 or 12 pull-ups. Every time you pull up, you have a chance of cutting into stronger air, the stronger wind. That is dynamic soaring. And you can feel the energy come on, the speed jumps. It means that when you pull up in a wave soaring situation, when you're trying to get into the wave, you don't handle the glider in the same way as when you're dolphin flying. Dolphin flying in thermals is something else. You know, dolphin flying in thermals is smooth, a lot of weaving, a lot of gentle pulling up and around place, around the core, on, gently. When you're pulling up into this, when you hit the lift, you go, whoa! And gradually accelerate away, and then you might be in the clean air, or you might fall down. Let's draw us falling down into the next slightly more vigorous thermal coming up the slope. Yeah? See what's happening there. So you fly along, boom, 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 bang, whoa! Pop, hang there, just try and fly off it. Maybe I'm in the wave. No. Next push, bang! So you actually pull up hard. You pull up steep and hard, and when you get down to a low speed, you just top over and you just hang. Hopefully, hanging in this faster and tilted flow that will start taking you up in the wave. So you try and pull yourself up. It's trying to pull yourself up with your bootstraps. That's what I'm trying to say. It's a motion of the glider which is very unlike normal dolphin flight. And it's very unlike normal soaring. This region here, the transition zone, what we call the rotor zone, I suppose. These are rotor thermals because they get rotated by the wind shear. This area is an area of rotor cloud. But I say, wave enhanced thermals here. This is a wave enhanced thermal because the inversion has gone up, stronger thermals here. And these I call the transition zone. And I try and not use the word rotor because when you say rotor, people are thinking of this, which it isn't. It's just individual vortices on the top caused by the wind shear. It's not doing that. Yeah, okay, so you pull yourself up, Having got in here, and I'm going quite fast because we only have a limited time to cover this, and I want to cover the big basics. Now you can see the profile of the wave because we described, you can see that. Yeah? In plan, here's the contour lines of this mountain. Okay? It's going to end here. Here's the cloud cover. I'm not going to draw this one because it's on the top of that, but here's the cloud cover here. Now the individual elements of thermals are blown back with the wind. Yeah? So there is a pattern of energy in that direction. If the thermal is solid, that pattern of energy may not be apparent, or it might look like this from above. Yeah? Because the wind's blowing that way, so each individual thermal, this will become this, will become this, will become this. Yeah? Okay, you will climb somewhere like this. And then you'll punch out into the wave. You might do something like that. It is quite likely that when you punch forwards into the wave, that you're in the best place, the steepest part of the streamline. It's quite likely that you've got in the best place available right now. Stay there. As you come through the shear between the underneath airflow and the on top airflow, the wind is quite likely to back here. It will be stronger and probably backed. Anticipate that. Turn the glider left just a few degrees. In the northern hemisphere, turn it right just a few degrees. Expect the upper wind to be like that if the lower wind is like that. Yeah? I've drawn quite a big shear there. Normally 20 degrees, something like that. That's what you'd expect. If you look from here at the top of these clouds, you look from there at the top of clouds forming, they'll be ripping off left to right with the shear. You see that really commonly, Mike? Okie dokie. You need to stay where you are. If the wind is strong, you can just hover. And you point the glider into the wind, and you look down over the side of the glider, you look down over the bathtub, over the side, like looking out the side of the bathtub trying to find soap that you've just dropped on the floor. And you try to see if the glider's slithering sideways. Because you're far enough from the ground that you can't look forwards and see by looking forwards, because the ground's a long way away. You're in the wave. Yeah? So you look over the side, and you're trying to get the glider positioned so that it's not slithering this way or slithering that way. So you work out the wind, and then you work out, if you're flying forwards fast, oops, I've turned the glider around. If you're flying forwards fast, then you can fly forwards until the wave peaks, and then go a little bit further forwards, then you can come back like this. Yeah? By circling. If you're moving forwards at a great rate, if the wind is light. I suggest today that circling technique won't be quite useful because the wind is light. So you go forwards and you find the best bit of the wave, and then you think it's dropping off, so I'll start to turn, and the glider does this. So you fly that path drifting back, forwards a little bit, back, forwards a little bit. And that keeps you in the same place. You don't lose it. You don't go away. What a lot of people do when they get in the wave is they go, oh, I'm in the wave now. That's no good. You lose it. Yeah, okay, so you want to stay there. If the wind is strong, you creep forwards and then you come backwards like this. Yeah? Beware using GPS moving maps. The GPS does not know your heading, it only knows your track. So the GPS will point the glider, if you're here, but going backwards, instead of being pointed in the direction you're pointed, the GPS will have the glider pointed that way, because you're going backwards. Yeah? Or it'll turn the moving map around if you've got track up. And of course the CU program nowadays attempts to compensate for the wind and give you a heading from your track, but garbage in, garbage out, guys. You know, it's treacherous. Don't just bugger off sideways as soon as you get in the way. Not unless you're really, really confident you know what's going on. Once you're established and you've worked out how far behind the feature the wave is, how strong the wind is, what orientation the wind is, then you can start thinking about moving. Now, there's a couple of principles I want to introduce you to before we go fly. Netto. Do we all understand what netto is? Okay. A netto vario tells you what the air is doing, not what the glider is doing. So if you're flying at 100 knots, but you're only going down at half a knot, you're obviously flying in lift. So an ordinary vario would be down. A netto vario is showing you the value of lift 5 or 6 knots up. You use the netto. You fly in the strongest lift. If you drift out of the lift, assume that you have drifted downwind and go into wind. If you make the mistake of assuming you've gone into wind, when you've done this, when you've gone this way, and you assume you've gone into wind, and you turn downwind, and you get that wrong, sink, 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 you have a hell of a thrunge back through sink to get back into the lift. On the other hand, if you've done this, and you make this assumption, you think you're behind the wave, and you go forward, you get a bit of sink, and you go, no, it's getting worse, straight back into the lift. The risk-reward balance is to say, almost every time you think you're out of lift, go into the wind first. So you use the netto and you fly along the wave path. The easy way to do it, if there's cloud or if there's a feature, is to keep a consistent distance back from the feature. Yeah? One other thing to say about following the wave let's say you're flying on lenticulars. So lenticulars form up, they're not cumulus, lenticulars form up. As the air flows up, you get condensation, and that condenses, and that's the trace of that streamline, and then here's the trace of this streamline, and then here's the trace of this streamline, and then here's the trace of this streamline. So a lenticular cloud forms, and it might be that sort of shape, with the wind blowing through it. So you're trying to punch from one wave system to another. Maybe there's cumulus underneath this, rotor cumulus, and rotor cumulus underneath this. It is an extremely dangerous thing to do, to come from here and descend into this. That may be solid, and that all looks fine, and you might be able to fly in cloud, but there's a mountain in it. You really do not want to be ever descending into the top of lenticulars. You don't do that. If you get a very good climb here, then you will have very good sink here. It just goes with the territory, doesn't it? If here's a very good climb, then here's very strong sink. So moving forwards from here to here can be fraught. In terms of moving around in the wave, what you want to do if you're trying to move forwards is this. Here's a wave bar, sorry, here's a mountain here, and here's a mountain here, and here are the wave bars associated with those mountains. I'm just giving you a very, very quick run through basic principles. I can't draw the tops of those. If you're trying to go upwind if you're trying to go upwind, then the place to move the glider from the climb, very good climb here, move here, no sink, no wave. Yeah? Find the spaces in between the wave. And what that says to you is fundamentally, actually, whenever you're making a jump between two wave bars, two wave systems caused by a different piece of terrain, you should always initially plan to be jumping forwards to maintain that position upwind. If you have the opportunity to take an upwind jump, take it. As a matter of course, always, rather than doing that, do that. Because it's really simple and easy to go from there to there, and it's an arse to go from there to there. So if you can go into wind, go into wind. So with the wind blowing across the country, wind blowing across the country from left to right, all these ridges may produce wave. Okay, let's look at what can do it. All those things have the potential to produce a decent wave. And here. This is a very good wave trigger. This ridge is a very, very good wave trigger. If you zoom out one more click, and okay, one more click again, or drag the thing down the page a little bit, so we can see Cook the other way around. Okay, Cook's up here. That's it, Cook's up here. Once we start getting more towards here, because of the fundamental shape of the country, which is the divide goes that way and the finger ridges come off it like that, as you work your way up to the finger ridges, if you're here or here, this is a little closer to the divide. As we come up and up and up, we're getting closer to the divide and probably in cleaner and cleaner air. And what tends to happen here is the convective layer here is quite thin. and the air comes across like this, and you're quite high in relation to that. So you tend to have better and better opportunities to get into the wave as you get further and further forwards, further and further forwards towards the west coast. The opportunities to get better and better. Here the thermals are very deep. Here they tend to be a bit shallow. And hopefully we'll be in wave by the time we're up here, and we're able to go and fly and cook and soar the summit ridge in the northwesterly and then come home in the wave. That's the plan. So we're trying to work lines of wave energy behind these hills. To get there, we probably can't climb here and then go and get in the wave here. We probably need some visible means of support. We probably need to go up here, through here, to get on these ridges in thermals, in these ridges in thermals, to possibly get in the wave here, possibly get in the wave here, possibly get in the wave behind this big ridge here or in here. But we need to get into the hills and up before we have a chance of contacting that way. That's a loose plan. Generally, when you're flying in flatland thermals, the arrival of a front is fairly bad news. You have this trough thing in Australia, I know, where the thermals liven up a bit. But generally, if you've got a front with proper weather on it, like a cool change, it's bad news, isn't it? When you get a front coming on here, it's good news because the wind picks up and the air becomes less thermic as the cirrus damps it down. I've made the mistake a few times in competitions of starting early because there's a front coming, and then of course as the front starts to arrive, the wave becomes very good and people go around the task really fast in the wave because I'm already home having gone really slowly in the thermals. So the effect of a front is to damp thermals down, but generally to improve the wave. There is an awful lot I can tell you about this, you know, and even I only have a partial understanding of it, so there's a lot more to deal with. But anyway, that's our goal today. We'll go and fly on the summit ridge in Mount Cook. I hope half a dozen gliders there. And if not, you know, you do what you can do. All right, get lunch and meet back here at 1:15.